Really, the main theme of the previous lecture was, how can we use recursion efficiently? So we're no strangers to the concept of recursion. We're no strangers to the concept of creating a recursive decomposition of a problem. And of course, if we're lucky, if we implement a traditional recursive algorithm that makes recursive calls to solve subproblems, we can get an efficient solution. What we saw last time, though, was that for some recursive decompositions, although the decomposition itself is relatively straightforward, if we use a traditional recursive algorithm to evaluate it, because there are overlapping subproblems in the recursive decomposition, we might end up solving the same subproblem over and over again from scratch. And the further down into the recursion tree that we go, the worse this problem gets, often resulting in exponential time algorithms where there might be a more efficient alternative. But in those cases, where we have a recursive decomposition, we saw that we could bring in an optimization technique called dynamic programming that allows us to break down the recursive structure of the problem and find some way of evaluating those subproblems in a more efficient order that results in a more efficient algorithm. Now, we also saw last time that so-called dynamic programming solutions to certain algorithmic problems often have a certain set of hallmarks or maybe stereotypes. So, for example, it tends to be quite common for algorithms derived via dynamic programming, or at least when somebody hands you an algorithm and says, oh, this is a dynamic programming solution, it's quite common to see, for example, a table of values used to store the results of subproblems that might need to be used again. And I took great pains last time to point out that although this is very common, and that is to say, in the last lecture, we used tables of values repeatedly, and in fact, in this lecture, both of the problems that we solve in this lecture use tables of values. That is very common, but that's more of a coincidence. So tables of values are pretty great. One of the reasons why a table of values is nice is that we get constant time lookups into the table. So if we need the result of a previous subproblem, we can get that result very quickly. So it's a bit of a stereotype that so-called dynamic programming solutions always use tables of values, but it is actually quite common to see that. What I really want to emphasize, though, is although it's fine that we often use tables of values, and they are a useful tool to use, it doesn't mean that somebody who gives you an algorithm that doesn't involve a table of values necessarily has given you an algorithm that wasn't the result of dynamic programming. And there might be a little bit of a bias in terms of where people use the name dynamic programming. That is, dynamic programming is a very general thing. There's a lot of different techniques that could factor into the optimization of processes the way that we did last time. And maybe it's the case that some people use those techniques but don't call the result a dynamic programming solution unless it looks like that stereotypical dynamic programming solution that we saw last time. So a table of values and a small number of, let's say, nested loops. And we're going to see in the next few lectures a few examples of algorithms where there's actually been a bit of a debate about whether the algorithm counts as a dynamic programming solution or whether it counts as something else. And maybe the reason for that debate is that some people look at the algorithm and say, this doesn't involve a table of values. How is this dynamic programming? And my point is, I think those people are really missing the point on this. Dynamic programming is a way of optimizing the evaluation of subproblems. There are lots of ways of doing that, some of which don't involve tables of values, and we can actually imagine cases where using a table of values might not be efficient. So a table of values is efficient because you get constant time lookup, but on the other hand, it requires a lot of space. It has high space complexity, and there could be cases where you don't want that, where instead it's easier to represent your system of subproblems by some other representation. So the thing to understand going forward is, although there's this stereotype that dynamic programming solutions always sort of look the same, that is to say a table of values and a bunch of loops, and we're going to see that stereotype does actually hold up quite a bit in practice, we don't want to accidentally trick ourselves into thinking that dynamic programming only applies in cases like that. Because our goal over the next few lectures, among many other things, is to sort of broaden our view of the ways that algorithms are designed and try and figure out whether there are, a set of different categories that a lot of algorithms fall into. I mean, algorithm design is a creative process, so you could design an algorithm that does not fit among any particular defined category in terms of algorithm design. But we're going to notice that it actually turns out a lot of the algorithms that we have seen and will see soon actually can sort of be divided up among key categories. For example, if you think back, we've covered a lot of divide and conquer algorithms. And I mentioned last time that I consider the divide and conquer algorithm to be the easy case of evaluating a recursive decomposition where subproblems don't overlap. You could still apply dynamic programming techniques to that in some cases, but often we find that traditional recursive algorithms do the trick anyway. I want to talk in this lecture a little bit about another type of algorithm called a greedy algorithm. And we're going to see, it's going to turn out that we've actually already seen a couple of greedy algorithms in this course. And I want to become familiar with this term, although it is a very general term, because often our first attempt to solve a problem amounts to trying a greedy technique. And that often it's the case that greedy techniques don't actually work very well, that it's relatively rare to find out that a greedy technique actually gives you the optimal solution. And then one other category that we should consider is dynamic programming derived algorithms, which benefit from a recursive decomposition, but one that is not evaluated by a traditional recursive algorithm. So in this lecture, I want to talk about two algorithmic problems. Both of them involves sequences. Now, of course, it turns out these work with sequences of just about anything, but for the convenience of giving a lecture with visuals, that is having slides, I'm going to use sequences of characters, so strings of text. But keep in mind that the sequences we work with today could be sequences of anything else. It's just that it's not as visually obvious when two sequences are similar if they're sequences of numbers or something else versus sequences of text. All right, so here's some sequences. We've got the word satin. We've got the word down here facing, and up in the middle, we've got the word fascinating. And it turns out that I can produce the word fascinating by interleaving the elements of the other two smaller words. And I guess I have to define what I mean by interleaving. I think it's a pretty intuitive concept. The idea is I want to take the two smaller words, and I want to take one letter at a time from each of the two words from left to right. I'm allowed to use multiple letters from the same word in a row. For example, I can take the F and the A in a row from the word facing. But what I basically want to do is to merge the two smaller words together in left to right order using every single character in both words to produce this larger word in the middle. So the larger word is said to be the result of interleaving the smaller word. If I can construct, let's call the larger word Z, if I can construct Z by merging together the sequences S and T, the smaller words, in left to right order. There's no requirement that they be interleaved one to one, so I can use multiple characters from the same sequence in a row if I want to, but I'm not allowed to use a character twice. So once I've used this H, it's gone. That means the next character I use from this string has to be the A. And I'm required to use every single character in both S and T. Now, a generalization that I might as well admit you ought to think about of the problem we're about to see, although I've defined interleaving to require that we use every single character from S and T, one generalization you could consider is, what if you're allowed to leave behind some characters in S or some characters in T? That is, you have to use the first few characters, but you can leave a few at the end that don't get used. How would you solve this problem then? So the algorithm that I want to develop is one that takes three different strings, so two small strings S and T and one large string Z, and reports whether or not I can somehow construct Z via an interleaving of S and T. And the first observation I want to make about interleavings is that if I ignore the middle string, if I just look at the two small strings, there are tons of different ways of interleaving them. So here's one way of interleaving them. So C, V, A, O, T, R, E, D. Okay, so I've interleaved the characters of those two strings. Here is some other way, V, O, T, C, A, R, E, D. There's some other way of interleaving those two strings. There are lots of ways of interleaving them. In this case, the algorithm I want to design is given a third string, so a specific string that is purported to be the interleaved result of S and T. You have to decide whether this truly is the result of interleaving S and T. And you don't get any of these arrows or the handy color scheme. You're just given the three strings, and you're asked, verify that the string Z. So is it true that the string Z can be created by interleaving S and T? Now, one thing we should consider right off the bat here is if I consider a couple of other string problems, I guess for the sake of an example, let's just cross this out again. I guess it is possible that the number of ways to interleave these two strings might not be very large. And if that's true, then I suppose I could test whether Z is the result of interleaving S and T by just looking at all the possible interleavings and reporting if one of them works. For some perspective on this, suppose that the question wasn't about interleaving. Suppose it was about concatenation. So in other words, is there a way of joining up S to T, end to end, such that we produce some third string? Well, there are only two ways of doing that. If I want to concatenate S and T, t, either I concatenate them with s followed by t, or with t followed by s. There's only two ways of doing it. So if I wanted to ask you whether a particular string was the result of concatenating s and t, you could just try all the options. There are only two of them. That would be an efficient algorithm for that purpose. There's no need to do anything more complicated. So the first point I want to make is the number of ways of interleaving two strings is very large. So that trying all possibilities, well, certainly feasible, I mean, you could do it, would likely take a long time. So given two strings s and t, which have these two lengths, n and m, the number of ways to interleave them is n plus m choose n, or n plus m choose m. So those turn out to be equal. Now, binomial coefficients are something we all know about, so the choose function is something we know about. However, I don't think that we've got much of a point of reference asymptotically for what it means. So that is, what is the complexity of n plus m choose n? To simplify things a bit, I could talk about the case where both strings have the same length. So where both strings have the same length, well then n plus m choose n reduces to 2n choose n, which is a bit easier to work with because there's only one variable involved. Okay, but what is the asymptotic complexity of a binomial coefficient like this one? So for this one here, where notice how the value on the bottom is basically half of the value on the top, and both values seem to be parameterized by n. If there was a constant on the bottom, things would change a bit, but the thing on the bottom is actually a function of n. It turns out it's exponential. Now, it's not actually big theta of this thing, so I just went looking for a bound that I could prove relatively easily that would demonstrate this point, that it is exponential, and I found this is not too difficult of a proof to write. Asymptotically, it's not actually equal to this. It's larger than this. But just to remind yourself that you can still prove big omega stuff at this point in the course, try this one out. So try proving that 2n choose n is big omega of 2 to the n over 4, which shows that it grows exponentially, which means if you wanted to decide whether or not z is the result of interleaving s and t simply by trying all possible interleavings, well, then you would have an exponential time algorithm. You'd have to try an exponential number of possibilities as the size of the two input words increased. So that's, I guess, some motivation for why we might want to try and develop a faster algorithm, because trying all possibilities isn't really going to be practical. So let's look at these three strings here. So I want to use these as my example because this has a little bit more ambiguity than the previous case. Because if you look at these three strings here, if I look at z and I ask the question, okay, the first character is p. I want to create z by interleaving s and t. Well, it's pretty clear that the p has to come from t here because there's only one p available and it's the one down here. So to create some ambiguity, let's look at these three strings. And the question is it possible to interleave the string lies and the string livens to create the string liveliness? Now, this could go either way. There are certainly strings I could give you in the middle where the answer is very clearly no. So, for example, if the string in the middle was way shorter than the other two strings, well, clearly you can't combine them together. So if the string in the middle had length 4 and the combined length of the other two strings is 10, well, certainly you can't interleave them. There aren't enough characters available. Similarly, if the string in the middle contains characters that aren't in the strings on the top and bottom, the shorter strings, well, then again, the answer has to be no. If there's no X, Y, or Z present in these two words, well, then there's no way you'll be able to interleave them. So there are certainly a lot of easy cases where we can rule out the possibility of interleaving. We can say the answer is definitely going to be no in those cases. So I basically want to focus on the cases that seem to be difficult, the cases where it's not clear that the answer is obviously no. The answer still could be no. Even with the right sequence of characters, it's possible that no interleaving exists. So the question is it possible to interleave lies and livens to make the word liveliness? What do we do to evaluate this question? Well, a first try might just be to generate an interleaving by working through our large string from left to right. So for example, I could look at the first character of Z and say, well, that's an L. Okay, well, I need an L from somewhere. Okay, we'll get it from S. There. S has an L available. We'll take the L from S. Looking good. So I go on to the next character. It's an I. Who can give me an I right now? Well, the character I can get from T is actually an L here. Okay, so T can't give me an I, but S has an I available because, of course, since I've used the first L, it's no longer, we just ignore it. So I take the I from S. Okay, so the idea here is what I'm doing is walking through Z from left to right, and at each step I need a particular letter, and so I go grab it from any string that has it available to me. And then I just work from left to right, and I hope that when I'm done, I have a valid interleaving. Okay, so we would typically call this mechanism a greedy approach. So there's that word that I used at the beginning. And the term greedy is actually sort of nebulous. Like it doesn't, there are lots of definitions I could give for it, and it sort of has to be tailored to a particular problem. A general definition that I think there seems to be a consensus on is that a greedy approach is one where at each step, in each state of the algorithm, as you try and make progress, what you do is make a locally optimal decision. So I need an L. I'm going to go grab an L from anybody that can give it to me because I don't know anything else besides that I need an L. I suppose if I were a little bit more clever, I could say I need an L and later I'm going to need an I. Okay, well, I'll take any L from a word that can give me an I later. But of course, both words can provide both an L and an I. So this is not the most obvious example of a greedy approach. We'll see another greedy approach later that I think would fit everybody's definition of the term. And the reason why I'm saying that is because I suppose you could argue that choosing the L from S is no more optimal than choosing the L from T. But the reason this is a greedy approach is that it is attempting to solve the problem by basically choosing at each point, at each decision point, it makes one decision, a locally optimal decision, and hopes, and emphasis here on the word hope, it hopes that a sequence of locally optimal decisions, if I choose to take one step at a time, I choose to take my step in what appears to be the best possible direction from where I'm standing, I'm assuming that if I keep doing that, I'm going to reach my destination eventually. But of course, that isn't generally the case. A greedy approach can fail in a lot of cases because the decision it makes at each step is a bit short-sighted. It makes what appears to be a good decision here, but later it might turn out that that decision was the wrong decision after all. Okay, so I pull in the L from S, I pull in the I from S, and then I get stuck. Now I need a V. Okay, but nobody has a V available. S can offer me an E, but I can't use an E, and T can still only offer me an L. Now, glancing at this, we both know that there's a V somewhere and that I guess I don't have access to it. But the question is, even if I did, would I be able to interleave these two strings? So it's pretty clear that I'm stuck at this point in my first try at an algorithm. But I guess the question I have to ask is the reason I'm stuck because this is impossible? Like, have I gotten stuck because there is no interleaving? Or have I gotten stuck simply because I had some bad luck and I've hit a dead end? And the answer is, well, who knows? I mean, in the absence of a proof, I don't quite know whether this greedy approach is guaranteed to find success. If it were guaranteed to find success, then any case where the greedy approach fails implies that there is no solution. Well, it actually turns out in this case that there is a way of interleaving these two strings, and that I just made a wrong turn. So early in the algorithm, when I decided to pull in the first L from S, that was the wrong decision. I should have pulled in the first L from T. And actually, and you can try this out, if I had done that, let's go back to the blank version of the exercise. If I had done that, if I had pulled in the first L from T, the rest of everything else would fall into line. That is, if I need an I have to take the I from T as well. Then I have to take the V from T, and then the E from T, and then I have to take the L. It turns out that the only place where I could have made the wrong decision is the first character, but that I did make the wrong decision there. Because my greedy approach, which tried to take one step at a time and just choose a step and then stick with it, well, it made the wrong decision. There is some ambiguity, and there was no way, from the point of view of this first character, to know which of the two strings I should take the first character from. And so what this is sort of telling us is, okay, if you want, you can try constructing interleaving from left to right, but you have to allow for the possibility that you might get stuck. And because getting stuck doesn't mean that you've completely failed, it doesn't mean that there is no interleaving, you have to allow for the possibility that when you get stuck, you might have to back up and try again. You might have to engage in backtracking. Now, generally speaking, we would not consider the greedy algorithm to be one that involves backtracking. That is, we might use the same heuristic that we are using for our greedy approach in a recursive backtracking algorithm, but typically a recursive backtracking-based algorithm wouldn't be considered a greedy algorithm. And so before we go any further, now, I mean, you know that we're ultimately going to tackle this with dynamic programming, but before we do that, pause the video and just think about this. So whether you actually write the code for this, I don't know, but think about this for a minute. Verify to yourself that you could write a recursive backtracking algorithm. So think back to the algorithms from lecture 12 to solve subset, sum, or partition. So a recursive exponential time algorithm that would solve the interleaving problem. Not only because it's good to verify that you can solve a problem in a relatively straightforward, if slow way, because it's better to have a working solution than a fast broken one, but also because it turns out that designing a recursive backtracking algorithm might get you well acquainted with the recursive attributes of this problem, with how the subproblems are structured, which can help design a dynamic programming solution later. Now, to be clear, the recursive backtracking algorithms one might design, so for the example, the one for subset sum or the one for partition, do leverage recursion, but they may not necessarily leverage a recursive decomposition of the underlying problem, and even if they do, it might not be one that's amenable to dynamic programming. So although recursion is involved in both cases, and although sometimes it's the case that you could design a recursive backtracking algorithm that you could then turn into a dynamic programming solution by analyzing the same recursive decomposition, it's not necessarily the case that it's the same skill set needed to design both of them. There are plenty of problems that you can't really tackle with dynamic programming, but that you can still design some kind of recursive algorithm to solve, because often the recursion isn't on the problem itself, it's on the structure of the solution or something else. It's basically a recursive algorithm to generate possible combinations that might form a solution. In any event, verify to yourself that you have some way of solving this problem, even if it might be slow, because as you've already seen, a dynamic programming solution, although it might be fast, takes quite a while to develop, and there are lots of steps, whereas a recursive backtracking algorithm can often get you to something you can rely on pretty quickly. All right, so I want to also emphasize why that greedy approach failed, and just show that this is not a problem where it is always as simple as simply saying, okay, well, as long as I can choose the right string to take the first character from, everything else will fall into line. In general, it turns out that even if you can pin down the correct prefix of an interleaving, you could still make a mistake halfway through that results in then later, getting all the way through here and having to backtrack. So it's not like once you've chosen the first character, everything else is going to fall into place. And I also want to emphasize that even if you were to allow yourself to backtrack and say, oh, the algorithm isn't going to be that bad if I have to back up by a couple of positions, I want to show that I can give you inputs where the amount you have to backtrack can be as long as I want. That is, I can make you an input of size 1 million where you have to backtrack 900,000 positions in some cases. So consider the case where both S and T share a long common prefix. And in this case, both of them start with the same 4 characters, A, B, C, D. And the question is, can I interleave them to form this string Z? Okay, well, Z starts with an A, and we have to be cautious here. So we already know that we could get ourselves into trouble. And so, I could say, well, suppose that A comes in from S, or suppose that A comes in from T. What I want to emphasize is, if I make the wrong decision, so suppose that I assume that the A comes in from S. Okay, well, if the A comes in from S, we'll just do this directly. If the A comes in from S, then I need a B. Well, the B has to come in from S as well. And then I need a C. Well, the C has to come in from S. And then the A has to come in from T. And then the D has to come in from S. And then the B has to come in from T. But then I get stuck. Oh, wait, no, one more step, sorry. And then I get stuck. So I bring in the C from T, and then I need an F. And I don't have an F available. The only thing S can offer me is an E, and the only thing T can offer me is a D. So what I wanted to show off here is that this long prefix, I can actually produce a string Z where it does look as if you're on a roll. It does look as if everything is working out. We don't get stuck quickly, and it looks as if the two strings are folding together so well that maybe we're fine, and then we get stuck really late in the process. Now, it turns out that if I'd made the other decision, if I'd brought in the first character from T instead, everything would work. Everything would just fall into line. So this is actually the same case as before to some extent, which is to say that it was just this one early decision that broke everything. But notice how I didn't notice that there was a problem until really late in the process. Making the wrong decision early on could result in me being able to fill up a considerable amount of the interleaving before I run into an error. And an exercise you can think about is see whether you can produce a combination of S, T, and Z of any length where you end up failing on the last character or the second to last character. You get almost all the way there before everything falls apart. And so hopefully this helps to illustrate that it isn't really as simple as saying, okay, I want to take the A from one of these two strings. Just look ahead by a couple of characters and see which one works out best. Because it could be that the two strings mesh together perfectly no matter which decision you make for a large amount of your output string, for a large prefix of your output sequence. I've just said some sort of nasty things about the greedy algorithm in this case. Now, there could be lots of different greedy approaches to this problem. I've only illustrated one of them, and I think it would be reasonable if you were to argue that I've chosen a sort of bad greedy approach, and that's why it has bad performance. And that's fair. There might be a greedy approach to this problem that is faster. The key thing that we understand for now simply is that a greedy approach is one that makes at each step just a locally optimal decision in the hopes that a sequence of locally optimal decisions leads us to a global optimum. And that can work in some cases. So for example, all three of the minimum weight spanning tree algorithms that we covered 2 lectures ago actually were greedy algorithms because the ultimate property that they leveraged, the cut property and the cut property construction theorem, actually were basically a greedy approach. It was at each step, if you have an incomplete spanning tree, whether that be a single tree or a forest of smaller trees, go looking for the minimum weight edge that meets certain criteria. So the minimum weight edge that you can add without creating a cycle. And that would be a locally optimal decision. In other words, from the point of view of this tree, the minimum weight edge is that one. And so I bring that into the tree. And the cut property tells us that if I do that, well, I guess the cut property and the cut property construction theorem together tell us that if I keep doing that over and over again, if the step I take at each point in time is to bring in that locally optimal edge, I will eventually actually have the globally optimal solution that I want, the minimum weight spanning tree. So the most obvious example of why this is a greedy algorithm, or why this is a greedy approach, would be to look at Jarnick's algorithm, because you have a single tree and you're choosing one edge that is the minimum weight edge leaving the tree. But it turns out that both Kruskal's and Beruvka's algorithms also actually could be considered greedy approaches. They're just making locally optimal decisions backed up by this theoretical property that tells us that if we do that at each step, we will eventually get the global optimum. But without a theorem like that, we can't generally assume that a greedy approach is going to work. But it's really common for people to start, when they first try and solve a problem, to start by trying out a greedy approach. And that's a healthy idea. It's good to try this out. Just remember to interrogate that approach enough. Remember not to buy into the idea that it works perfectly until you've tested it a lot, and then, of course, gone and proved a theorem. Okay, so one other thing I should say about the greedy approach is the particular greedy algorithm that I just described actually works perfectly in some cases. So we can define special cases of this problem where the greedy approach works just fine. One such special case is the one where our strings S and T contain disjoint sets of characters. That is, they have no characters in common. This is not the only case where the greedy algorithm works, but it's the easiest one to justify, and so the exercise is to go right ahead and prove that. I can give you a sort of overview of why that holds. Consider the first character, H. Well, I need an H from somewhere. Where can I get it from? Well, T has an R and S has an H. Well, I have to take the first character from one of them, and only one of them gives me the first character, so it must come in from S. And then I get to the second character, and it's an A. And basically, notice how at each step, because S and T contain completely distinct sets of characters, the character I need at each step can only be in one of them, and that will be the correct one if interleaving is possible. And therefore, if you have 2 strings that have disjoint sets of characters, the greedy approach will work if a valid interleaving exists. And even better, it actually does this just by going from left to right, and therefore it does it in linear time. So n plus m, well, that would be the sum of the lengths of S and T, but actually the length of Z is equal to n plus m, because it's in the event that it can be interleaved. So obviously, if we discover that the length of Z is not n plus m, then the answer is no, we can't interleave them. All right, so the question now is, I guess we've seen that a couple of obvious attempts don't really work. So using this greedy approach doesn't really help us in general because there's ambiguity. So in the event where the 2 strings begin with or end with the same character, the greedy approach might make the wrong decision. We consider the idea of solving it by brute force, that is generating all possible interleavings and see if any of them matches our middle string Z, but then we observe that there are an exponential number of such interleavings, and so that's not a great idea either. Okay, so what can we do? Well, let's try dynamic programming. Is there a recursive decomposition that we could leverage to use a dynamic programming optimization process? And the answer, of course, is going to be yes. It's actually something that we've already seen. So consider this case here. Now, of course, earlier when I was talking about breaking down the interleaving, I was going from left to right because that's sort of the natural order for people that speak English. However, I'm now going to begin going from right to left, from the end of the sequence backwards. This This is because in preparation for using dynamic programming, for similar reasons as why I did the same thing for the subset sum problem last time, it's actually easier just to go from the end of the string backwards, basically. Or it's easier for me. I mean, you could do it either way, but the indexing works out better if I'm going from large indices down to small ones. Okay, so the last character is an S. And certainly, as I've just observed, notice how the two smaller strings here actually have disjoint character sets, which means that the greedy approach would in fact work just fine, and that's because that's deliberate. I just want to start from a relatively straightforward example. So the greedy approach would be able to tell us that the last character S does come from the string T. Okay, fair enough. That actually isn't the thing I wanted to observe here. What I wanted to observe is that once you've done that, once you've locked in that the character S must come from the string T, you can basically ignore that character. It's been locked in. Now the question is, how do I produce the rest of the interleaving? And what I notice is I'm basically just solving a recursive subproblem. I want to know now whether I can interleave the word mild with the word see to form the word mislead. In other words, I want to interleave smaller strings, or one of my two strings is now smaller, to form a smaller version of Z. And that looks a lot like the beginnings of a recursive decomposition. So in other words, I can interleave mild and sees to form misleads only if I can find some way to interleave mild and see to form mislead. Now, what about this situation here? So these are the strings that have some ambiguity. Lies and livens, and the middle string is liveliness. Okay, so if we go to the end, if we look at the last character of this string, the problem is that it's an S, and both other strings could give me that character. So what do I do? Well, if I were using a greedy approach where I have to lock in the value of this character right now, then I might make the wrong decision. But I'm not doing that. I'm just developing a recursive decomposition. And I'm allowed, as we know, in a recursive decomposition to make multiple recursive calls if I need to. So why don't I do that? There are two possible places I could get the S. I could get it from up here, or I could get it from down here. I could just use, I could consider the recursive subproblem that arises in either case. Okay, so case one, in the event that I take the S from the first string, the string on top, well then this reduces to the subproblem of deciding whether there is a way to interleave the string lie and the string livens to make the string, live lines. Okay, so that's one case. Case two, in the event that I take the last character from the string on the bottom, then the subproblem I want to solve is to figure out whether there is an interleaving of the word lies and the word liven to make the word live lines. If either of those subproblems come back with a positive result, if there is a way to produce the interleaving of lie and livens or the interleaving of lies and liven, well then I could take that and turn it into a solution to my general problem of interleaving lies and livens to make liveliness. Now, I want to create a recursive decomposition. I want to state a recurrence, but I can't do that yet because we're talking about strings. Now, we can treat a string like a sequence. I can say my string S is equal to C1, C2, C3, whatever, up to Cn, and that's all well and good. I could easily do that. The thing is, I want to begin talking about things like subsequences, and if I do that, well, that's fine too. I could say, let's consider the subsequence Ci, Ci plus 1, all the way up to, I don't know, Cj minus 1 or something. But I'm going to be working with enough substrings and subsequences today that I'm going to need a whole ton of index variables if I do it that way. And that's going to make a huge mess. So I guess I need to develop some more compact notation for that. So the notation I'm developing here is just for visual convenience. That is, we could just use old-fashioned mathematical sequence notation, but it would be very dense. I have a slide later on that uses that notation that I think helps to prove this point. So what I'm going to do is just introduce some basic notation for strings. So first, I'm going to let this symbol here, this epsilon, denote the empty string. So a string with 0 characters. Then I'm going to use this symbol, as we'd expect, to denote the length of a string. Note, of course, that the empty string has length 0. I don't know that I actually need this definition in this lecture, but just since we're here, I'm going to define the plus operation to be concatenation. So if I have two strings and I do S plus T, then I'm concatenating those two strings together, just like in your favorite programming language, assuming your favorite programming language is not the C language. And then finally, I want to talk about strings and substrings. Basically, I'm just going to use Python-style notation, but I have to define that mathematically, so here it goes. First, I will use zero-based indexing for the characters in my string. This is going to produce a little bit of a snarl later in the lecture, but we're better off doing it this way than the alternative, and also it does make it easier to implement this in a language with zero-based indexing. That is, switching to one-based indexing for this one lecture wouldn't have been worth it. So suppose I have a string, and these are the individual characters of the string. First, I will allow the use of square bracket indexing notation. So S sub I is going to evaluate to the character Ci. And also, I'm going to use this Python-style range notation to denote substrings. So if you give me two indices, and actually I think maybe we'll say that they can even be up to n here for reasons that'll become clear in a minute. If you give me two indices, the notation S of I colon j denotes the substring that contains every character from Ci up to but not including Cj. So it's an open-ended range where character j is not in the substring. This is as in the Python programming language. Now what this means basically is that, or I guess whether this is implied by the definition or I'm just defining it separately, I guess is up to you. But one implication I claim of this is that C of I colon j is always the empty string in the event that I happens to be greater than or equal to j. In particular, if I were to ask for something like S of 5 to 5, then this is saying give me every character from character 5 up to but not including character 5. So this actually turns out to be the empty string. It turns out to be nothing. And I've got some examples on the next slide here. Okay, so here's a string. It's the word raspberry. It has 9 characters numbered C0 through C8. If I do indexing, S of 3 would give me the value of C3, the letter P. S of 4 through 8 would be every character from C4 up to but not including C8, which would be BERR. S of 1, 4 would be every character from character 1 up to but not including character 4, so ASP. And finally, S4, 5 would be everything from character 4 up to but not including character 5, so just a single character B. As I mentioned on the previous slide, if I were to ask for something like S of 5, 5, that's going to be nothing. That's going to be the empty string. And just to drive the point home, if I ask for a range that's inverted, so for example, let's do S of 5 to 1, well, I can't count up from 5 to 1, so that's also going to be defined to be the empty string. I could argue this should be an error or something, but it doesn't hurt us for our purposes to define it to be the empty string. That is also consistent with the sequence-style notation we're importing here from Python. All right, so I now know about strings, and therefore I have enough notation now to be able to compactly define a sort of recursive decomposition for my interleaving problem. And I'm going to do this using the same technique we saw twice in the last lecture, which is that I guess ultimately what I sort of want is to know how to interleave S and T. Although the original problem was just tell me if I can do the interleaving, it is going to turn out that I want to know how to interleave S and T. But before I get there, I'm going to start by simply reporting whether it's possible or not. I'm going to define a recursive decomposition in terms of a very convenient output of just true or false. I'm going to make a table of subproblems of can they be interleaved or not. And then I'm going to reverse engineer those simpler subproblems to actually figure out what the interleaving itself is. So this is a technique we've seen in the last lecture. It's one of those stereotypical dynamic programming techniques. There are plenty of solutions to plenty of dynamic programming algorithms you can come up with that don't use this technique, but it is quite a powerful technique. Develop subproblems for a relatively simple version of the thing you're solving, and then reverse engineer those subproblems to find the solution you actually want. Okay, so for 3 strings, S, T, and Z, you give me those 3 strings. Once I have them, I will now define a Boolean function aij to be true if I can interleave the first I characters of S and the first j characters of T to form the first I plus j characters of Z. So I know it's sort of a strange way to break down the indexing, and also that where is this I plus j coming from? So notice that what I'm trying to do here is interleave the first I characters of S and the first j characters of T. The only way those will interleave together, I mean, obviously if I interleave them together, I'm going to get something of size I plus j. So the only time that I care about a particular substring of Z here would be the substring 0 through I plus j. Now, ultimately, the problem I'm now solving is I want to figure out whether I can interleave all of S and all of T to form all of Z, which means I'm really asking, is this number, A of size of S, size of T, is that true? And so if that's true, then it is possible to interleave S and T, the entirety of S and the entirety of T, to form the entirety of Z. Also a reminder that these substrings, S of 0, 0 and T of 0, 0, are empty because when I use this range notation, if the beginning and end point of the range are equal, then I end up with the empty string. Okay, so I have enough now to begin stating a recurrence form for my function A. Okay, well, the base case is, the base case, I guess, can be broken into three pieces. A purist would actually argue that I only actually need this base case. It turns out later I'll be able to condense these two other base cases into a sort of special case of the recursive case. I don't actually need to call them base cases. But for the sake of designing the recurrence, it's way easier, I think, to call these things base cases, specialized base cases. Okay, so the first base case, the one that everybody would agree we have to have, is that A00 is always true. So A00 is the question, is it possible to take the first 0 characters of S and the first 0 characters of T and create the first 0 characters of Z? And the answer, of course, is always yes, because the first 0 characters of S, that's going to be the empty string. The first 0 characters of T, that's going to be the empty string. And the first 0 characters of Z is also the empty string. And it's always possible to interleave the empty string and the empty string to create the empty string. So A00 is always true. Now, what about A0J? What that's asking is, can I interleave the first 0 characters of S and the first J characters of T to form the first J characters of Z? Well, obviously that's only going to work if all of the first J characters of T equal the first J characters of Z, because I'm not allowed to pull in anything from S. So it's true if the first J characters of T equal the first J characters of Z and false otherwise. And then base case 3 is just the symmetric version where J is set to 0. So I want to take the first I characters of S and the first 0 characters of J and interleave them to form the first I characters of Z. So I get this symmetric case to base case 2. Okay, so that brings us to our recursive case. For our recursive case, if both I and j are greater than 0, well, then A of ij is true if either of these conditions hold. So these conditions are long enough that I wanted to write them separately, but we could view A of ij as being sort of a logical OR of these two conditions, I guess is the best way to think about it. Okay, so basically the idea is this. If I'm trying to interleave the first I characters of S and the first j characters of T to form Z, well, then let's just look at the end of what I'm working with in both. So let's just draw quickly an example here. So suppose S of 0i is equal to A, B, C, D, and T of 0j is equal to E, F, G, H. And then in the middle I've got Z, and we of course really only consider Z up to character I plus j. And suppose that equals some stuff followed by the letter D. Okay, well, if so, then the interleaving has to be, clearly, if I need a D, the D has to come from S here. So that would be the first case. So if the last character in my substring of S equals the last character I'm working with from Z, well then take that character off of both of them, and now look for an interleaving of all of what I have of T, so T, the first J characters of T, but then the first I minus 1 characters of S, and then to interleave to produce the remainder of Z. So that would be the first of my two subcases of the recursive case. Now the other option would be, which is the second bullet point, is suppose the last character of Z is an H. Well, then the H has to come in from T, so what I'm now working with, the recursive subproblem that I'm solving, is the one where I get rid of this H, and I'm now trying to interleave the remaining characters of this substring of T, so up to character J minus 1, with all of the characters of this substring of S, so up to character I minus, or up to character I, and to form the rest of Z. Okay, so I have these two cases. Now, the case we have to consider, the one that makes the problem difficult, that makes the greedy approach fail, is what if both of the substrings end with the same character, and that's the last character of Z? Well, if that's the case, then either of them could work. Like, we don't know in advance which of them might produce a valid interleaving. Maybe neither of them do, maybe both of them do, maybe only one of them does. So what I'm doing here is simply saying, look, if I could find an interleaving in the case where I take the last character off of S, then that way would work. If I can find interleaving in the case where I take the last character off of T, well, then that would work as well. So that's why it's a logical OR of these conditions. Maybe both cases are true, maybe neither case is true, but I have to consider both cases. That leads us to this very, very ugly looking recurrence. Okay, so I mean the first three lines of it look just fine. Those are our three base cases. Here is the recursive case, written as a single logical expression. Now, it is partially, the reason it's this ugly also has to do with the way I've broken it down. That is, if I were to take a bit of this and make it into a conditional on this side, I could break it down into more formulas, more lines that are simpler. But ultimately, the recursive case is going to be this complicated either way. So what I've basically done here is I've turned each of the bullet points of the recursive case into a logical formula. In other words, this is going to be a true or false answer by itself. Here is a conditional expression, and there's a logical and. And then I've taken those two logical formulas, and I've tied them together with a logical or. And if I write that with fancy mathematical notation, here is my logical and operator, and there is my logical or operator. So really, this is just what I've written on the previous slide, but turned into a logical formula. Now, it's interesting because I actually find this to be sort of horrifying. Like this formula is very hard to understand. I think that that's to do with a certain bias on my part, and I'll come back to that in a few slides. I can turn this recursive expansion into pseudocode. So I could leverage the fact that I realize that the index that I care about, so the problem I actually want to solve is this one, a of size of s, size of t. And I noticed that, okay, if the size of s is n and the size of t is m, then really the set of subproblems I'm solving are just values of a, I, j, where I is less than or equal to n, and j is less than or equal to m. And I could just store all the values of those subproblems in a table, so here comes a table of values again, and that's basically what I do in this pseudocode. So I make a table of Boolean values, and then I just evaluate from the base cases working my way upwards. I just evaluate every value of a, and then return a of nm. And we can, so a of nn here would equal a of size of s, size of t. And we can observe that this has running time, which is big theta of n times m, for two reasons. One, that it creates this table of size more or less n times m. So it also has n times m space complexity. And then I've got these two nested loops that have running time n times m. And everything else is pretty much constant, although maybe that part isn't. I'll come back to these two lines in a minute. They're not constant necessarily, but there's something that we can get out of. We're going to rewrite the code a little bit to get around this. Although even in its current form, the algorithm is still a big theta of n times m. Okay, so this is pretty ugly looking. I really don't like this formula sitting here. It feels like it's hard to understand the algorithm because of how long this formula is. I want to try and tackle that, but first I want to address the situation happening in these base cases. So the issue here is that what I have here is a loop that's going up through all values of I from 1 up to n, and then setting up the value of this base case. So remember that a of I comma 0 corresponds to the case where the first I characters of s match perfectly with the first I characters of z. The issue is this equal sign here is doing a full string comparison. That is, I'm actually asking the question, let's look at I equals 5. I'm asking the question, does s of 0 through 5 equal z of 0 through 5? And of course, we can answer that by iterating over the strings up to index 5 and then deciding whether they're all equal. And it's fine to do that comparison. The issue is that on the very next iteration, so suppose I figure out that s of 0, 5 is not equal to z of 0, 5. On the very next iteration, I am then asking this question, is s 0, 6, is that equal to z of 0 through 6? And wouldn't you agree that I already know the answer? I mean, if I know that s of 0, 5 isn't equal to z of 0, 5, then of course s of 0, 6 is not equal to z of 0, 6. But also, whether I knew that answer or not, isn't this going to be duplicated work? I have to do a string comparison of a bunch of characters, then I do a complete string comparison of the same characters plus one extra character. It feels like I could make that a bit faster. And so there is a way of doing that. What I could do is observe that because I've already compared characters 0 through 5, all I really have to do at step 6 is look at character 6, or look at the next character, and then just add that into the result I got from the previous iteration. So I could do something like this. I could say, and the reason it says I minus 1 here is because there's an offset in the indexing. Remember that Aij is the question of whether I can interleave s of 0 through I, which the last character in this substring is actually index I minus 1, with t of 0 through j, which the last index of that substring is the index j minus 1. So we'll notice as we go forward here that there's a few cases where a minus 1 shows up, and we're actually talking about step I, because the value of I is the length of the substring, and the last valid index of that substring is therefore that minus 1. So what I can do with the base case is I can turn the base case into comparison of a single character, s of I minus 1 to z of I minus 1, and a logical and with the previous base case, so the one that's one row up. And in so doing, this now is actually a constant time line versus a line whose time was proportional to the size of the substring, which could actually be big theta of n in some cases. Okay, so I've cleaned up the base cases a little bit, and that does actually clutter the code a little bit more, although it does speed it up. There's still the question of what do I do with this horrifying logical formula? To me, this long logical formula makes the code very hard to read. And here's where I should talk about a bias that I have. I think the reason that I feel that way has to do with the fact that my background, and probably your background too, so I would say at least 75% of the people that watch this probably agree that this formula doesn't make the code any easier to read and might prefer something that looks more like this. So here what I've done, basically, is inside of the nested loops, what I observed was I have a logical OR, and so I could take this logical OR and split it into two pieces and use if statements to represent those pieces. So this conditional, I could make the condition of an if statement, as with this one, and then inside the if statement, I can bring in the other value of the logical and. And you'll observe that's sort of what I've done here. I've just added this if statement, and this is the same formula. Ultimately, I'm actually doing exactly the same work. A compiler might turn both of these into the same thing. However, for some reason, this code looks cleaner to me. And I think the reason for that is, and as I said, about 75% of people I suspect would probably agree with me, that we all have a common background where the first programming languages that we learned were imperative style languages where we execute the code, in a sequence line by line and we do assignment statements. And therefore, this code just looks more natural to us. If we had learned as our first programming language, I don't know, like a logic programming language or a functional programming language, then maybe this big formula wouldn't be a big deal. So it might just be that the reason I think it looks ugly is more to do with my comfort zone than anything else. But anyway, here is the version of the algorithm that I would probably work with if I had to write this myself. It's the same recursive decomposition, but I've boiled it down to something that's a bit simpler code-wise. So not only have I split that long formula into two pieces, notice how I've also gotten rid of those two separate loops for the base case. So these loops are gone, and the reason I can get rid of them is if I stare at this for a minute, what I notice, if I look at, let's say, this formula here, this looks a lot like this formula for the case where j equals 0. So what I could do is basically just turn this loop, I could fold this loop into this loop here with the addition of one extra little guard here to make sure I don't do -1s when I'm not supposed to. And that's basically what I've done. So I've combined everything together. It might have actually added a little bit of overhead to combine them, but doing it results in a much simpler, in my mind at least, a much simpler flow of control in my algorithm. So now I can use this algorithm to develop a table of values for my Boolean function a. And so I guess now the question is, suppose that you have that table of values. So I've got the word mild, and I've got the word C's, and I happen to know, because entry 4 of the matrix is true, I happen to know that there is a way of interleaving them. So the question is, can we find the actual interleaving sequence? Can I find where I get each character from? Can I find a mapping of the characters of S and T into the characters of Z? And the answer is yes, I can. Just like I did in the previous lecture, I can take this table of values for subproblems and, in a sense, reverse engineer it to figure out the mapping. So before I go forward, I'm going to make the same observation I made a few minutes ago. This is going to come up again later in the lecture, which is that there's a bit of an indexing snarl here. So remember, again, that A of, let's do A of 4. This is asking the question whether the substring S 0 to 4, and notice that the actual indices of characters in S only go up to 3. The substring S of 0 through 4 can be interleaved with the substring T of 0 through 4. So notice that the values I and J are actually one index above the corresponding characters of S and T. So the character that I'm pulling in from S at step, when I'm talking about A44, the thing that makes A44 true is that, it's actually coming in from T, is the fact that I can pull this character in from T, even though this character is actually at index 3, index J minus 1, not index J. So sorry about that. I know that's going to make things more complicated. Shifting the indexing to do something different there wouldn't have made anything easier. It would have just made the base case more of a hassle because the base case would occur at index -1. And on balance, I decided that the weird off by 1 error happening with using J minus 1 or I minus 1 for the string indexing is probably easier to digest than the case where we have negative indices in our table of values, which is really weird. So we know that A44 is true, so there is some way of interleaving these strings. And now the question is, can we work backwards from that to find the interleaving sequence? Okay, so what we do is what we did last time, basically, which is we use our knowledge of the problem, we use our knowledge of the input strings, and we use our knowledge of the recurrence to figure out what it means for A44 to be true. So I know that A44 is the result of a logical OR operation involving other subproblems. And if we look at the recursive decomposition, we realize that the logical OR that produces A44 involves the value of A34 and the value of A43. At least one of those must be true in order for A44 to be true. To be clear, other conditions also have to apply, but certainly at least one of those has to be true. What I notice is this one is false, which means the reason that A44 is true is because A43 is true. And if I look at the table, it's sort of clear what A43 means, because the subproblem A44 is telling me that I can interleave the strings mild and C's to form misleads. If I ignore column 4 and I look at the table up to column 3, A43 is telling me that I can interleave the strings mild and C to form mislead. So it's telling me what subproblem I can leverage to interleave the entire string. So what that's basically saying is, since I'm chopping off this character here, that's the last character of T, that must mean that the last character of T is getting locked down as part of the interleaving. So the S gets mapped in from the string T. Okay, so T4 gets mapped to index Z8. And actually, I think this is the slides are actually indexing this wrong. It should be S3 and T3. So sorry about that. Okay, so then the next step is I notice when I'm looking at subproblem 4.3 that I have to go up one step to find a true subproblem this depends on. The thing to the left isn't true. Okay, so what that's telling me is that the reason I can interleave mild and C is because I can interleave mill and C to form mislead. And so that's telling me that I take the next character from S. I take the D from S. Maybe you're already seeing a sort of pattern here, which is that which character I take at each step really can be reduced down to the question of, do I walk to the left or do I walk up on my way to my solution? Okay, the next character is A, so I'm walking over to the left in this case, and that's telling me that there is a way of interleaving SE and MIL to produce misle, whatever that is, so therefore I can bring in the next character from T. Then I walk left again, so I bring in the next character from T, and hopefully you can see, if I walk left, I'm taking a character from T. If I walk up, I'm taking a character from S. So I walk up, I take in a character from S, then I walk left, take a character from T. Now I could continue, I could keep walking up in the matrix, and then I could pull in 2 more characters from S, but I guess I would argue that for our purposes, reverse engineering the recurrence versus actually writing code to do this, for our purposes, I think we're done, because this is actually a base case. So once we get a base case, we don't actually have to keep crawling through the matrix, we can just stop. So the base case I end up at here, which would be 2, 0, this is the base case corresponding to the first few characters of S matching up with the first few characters of Z. So because the index J is 0, I'm not allowed to use any more characters of T, which we can observe because I've used up all the characters of T. Because I know that an interleaving exists, because my original value A44 was true, I therefore know that the only way to produce an interleaving is by just bringing in all the remaining characters of S as the first few characters of Z. Okay, so there's my interleaving sequence, and we can verify it is indeed correct. It is a way of interleaving those 2 strings. Now, as the slides are late to the party as usual, as I observed halfway through, it does turn out that the interleaving sequence corresponds to a path in the matrix from the lower right corner all the way up to the upper left corner, a path that I will call monotonically increasing, because if we take the path from left to right, the indices I'm looking at each step always increase. So I wouldn't be allowed, for example, to use a path that went like this. That wouldn't be allowed. The value of I has to either increase or stay the same, and the value of J has to either increase or stay the same at each step. So a valid interleaving sequence corresponds to a path through the matrix using only true entries in the matrix, where it's a monotonically increasing path. Now, and so also as we observed, if I look at the path from left to right, on a step that moves downwards is corresponding to a case where I take the next character from S. So if I look at this path all the way from the upper left corner, the first couple of steps are downward, so I take the first 2 characters from S, then I move left, then I move to the right, which is the first character from T, then I move downwards, which is the next character from S, then I move to the right 2 steps, so that's pulling in 2 characters from T, and so on. And hopefully it's clear that for this particular problem, problem, it reduces to quite a nice intuitive, big visible property in the matrix. We know already that, the way that we tackle that depends on the problem, that the dynamic programming that we're doing partially involves how I interpret the results, so a way of analyzing the results. But in this case, it's actually quite it's actually just finding a path inside of the matrix. And I should also observe that this is a table of values, and that's all great, but deep down, the path I'm really finding is a path in a graph. That is, this table of values is a way of representing a particular graph, representing in a compact way truth values corresponding with nodes of a particular graph, and deep down, the path that I'm finding is actually just a path in that graph of subproblems. All right, let's now tackle this harder input from earlier. I want a way of interleaving the strings lies and livens to form the string liveliness. And here is the matrix that I get. Now you'll notice that in this matrix, there actually are multiple paths I could take. So here's one. So it's one that goes up first and then it goes over. And this is the one I think that the slides are going to want to take. But I could also do this. And that's valid. Any path that takes me from the upper left corner, entry 0, 0, all the way down to the lower right is going to work. It's fine. However, as I observed in the previous lecture, if our goal is to find an interleaving sequence, we don't have to find any particular path in this case. We can just find any path. And so if we always choose the same one, if we always go up when we have the choice, then that's fine. Although the fact that there are multiple paths implies there may be multiple ways of interleaving these strings. And that turns out to be the case, and I'll even show you where that's happening. These last two S's, I can pull these S's in from either of the two strings in either order. That is, there is a way of interleaving them where the last character comes from the first string, and there's a way of interleaving them where the last character comes from the second string. Both are valid interleavings. This isn't true of the first characters, so if I were to go from start to finish here, pulling in the L from one string could lead me into a dead end versus the other, but with the last two characters, they can come in either order, and that's reflected in the fact that if I reconstruct the interleaving sequence for either of these two possible paths, I will get a valid interleaving, and it will correspond to the two different ways I could pull in those last two characters. Okay, so in this case, I start at the lower right corner. I notice, although it turns out I could go either left or up, I choose to go up, and that corresponds to taking a character from the string lies. So I pull in the S from the string lies. I'll just tell you at this point, let's just ignore the indexing being used by the slides in this example, because I think these indices are off by 1. Okay, so then I pull in the next character. I have to go to the left here, so I pull in the next character from T. And then I'm going to skim through the rest of the example because I think it's relatively clear. I have more examples than I need in these slides for review purposes. Okay, so we just pull that in. Eventually, we hit this base case. Now, although we could just crawl all the way back to 0, 0, again, for the sake of reverse engineering the recurrence, we're now done. This is a base case. We pull in all remaining characters from the string T because no characters are left in S, and it's clear they all have to come in from T as a result. Okay, what about this one? Okay, so I'm going to go through this one very quickly. What I want to show is that in the matrix, there are clearly a whole bunch of different paths. So I could go like this. There's one path. I could also go, let's see, like this. There's another path. I could also go like this. So there are tons of different paths. There's at least one more path. I forgot which ones I've already listed. So there are tons of paths through the matrix, which means there are going to be lots of different options for an interleaving sequence. But our reconstruction is still the same. I just work my way up from the bottom right corner. And because I'm starting down here, I am guaranteed that no matter which direction I choose at each step, I will not hit a dead end. Dead ends could arise if I worked my way downwards from the upper left, but they won't arise if I work my way upwards from the lower right. And if you think about it, that makes sense because this is true because one of these two things is true, or both of them. And whether I go left or I go up, well, this is true as well, which means if there's a true value in a particular cell, there must exist a path from the upper left all the way to that cell. So no matter which cell I choose to go into next, as long as its value is true, a path still exists. So if I go over here, a path still exists. And that means that no matter which way I work my way back up, I will always find the upper left corner. Okay, so we'll skim through this just to find the path. There it is. And so we find this interleaving sequence. A good exercise is to go and generate some other option because you can see that there are a variety of other paths that I could take. What about this one here? So here's one where both of them share the same last character, but they have this long common prefix. and we'll see that the matrix breaks into these sort of clusters of t's, of true values. So a path I could take, I think the ones the slides want to take would be this one, but I have a variety of other paths. Once I get into one of these clusters, how I navigate the cluster can vary. I've got lots of different ways to navigate the cluster. In particular, this one up here, I could go all the way up and then over, I could go all the way over and then up, or I could sort of take a diagonal approach, or I could even take a different diagonal approach. All right, so the slides are going to want to basically prefer going up versus going to the left. Okay, so there's the Z, there's the other Z, and maybe we can observe that because of this cluster, I could actually have pulled those two Zs in either order. And so we navigate our way all the way up to a base case. Okay, so there it is. And then we pull in all the remaining characters from T because we hit the row where the index into S, the index I, is 0. And so we've got one possible path that we just produced. It would be this path here. But there are lots of others. And in general, if there are more paths, then that's telling you there are other distinct interleaving sequences. And so it turns out if I take these three groups of characters, the W's, the A's, and the Z's, I actually can bring in those characters in either order. So among the four A's, it makes no difference which order I pull them in from S and T. And that actually explains this cluster of true values in the matrix here. It's telling us that it doesn't really matter that much what order you pull in the initial sequence of A's. And so here's another path that takes, I guess, the more diagonal looking path. Now, I want to talk more about this idea that since I started at the lower right, I'm guaranteed to find a path. I think I already justified why I know there is a path if I go from the lower right back up. If I solve all the subproblems, produce the matrix, and then work my way back up through the matrix to find the interleaving sequence. But I suppose there's an instinct you might have to say, hey, wait a minute, now that I've figured out how the problem works, now that I've reduced the problem to finding a certain type of path, maybe I don't need the matrix at all. Maybe I could just, start walking at the upper left and then walk my way down through true subproblems, building, I guess, from the top down rather than the bottom up. Why bother with the matrix when it turns out the matrix just contains this one path? I've got lots of wasted space inside the matrix. So I want to illustrate why we do need the matrix. I need to have the entire matrix of subproblems. I need to have the value of A44 and work backwards from it, or else I could get stuck. If I just try and find a path from the lower left, then what is stopping me from navigating all the way out this way? In other words, if I begin finding my path from 0, 0, well then maybe I keep looking for values that are true and I say, hey, it looks like I can go right. It looks like I can go right again and again. And then I end up over here, which is a dead end. Although this happens to be true, none of the subproblems that depend on this end up being true for other reasons. That is, the characters in question don't match up. And if I follow this path, if I end up in this situation, that corresponds to this partial interleaving, where I've managed to pull in a bunch of characters from T, but then when I'm sitting here, I have no options. The only character I can pull in from S is the character E. The only character I can pull in from T is the character I. And so I'm out of luck. And this is actually also an illustration of why that greedy algorithm didn't work. The greedy algorithm assumed that as long as I can keep building my interleaving sequence, that there will be a good outcome. And although that may be the case, so if I dial it back a bit, if I'm sitting at the character D here, if I make a different choice, I can actually see some success. But if I make the wrong choice, I could end up hitting a dead end and having to back up an arbitrary number of positions. As I said earlier, in this case I have to back up by 3 positions, but we could create input sequences where you have to back up by thousands of positions if you make the wrong turn. And it's not obvious if you're navigating in this direction when you're going to make a wrong turn. Whereas if you're going backwards, it's much easier because there might be multiple ways to go all the way back, but every way will lead you all the way there. You'll never see a case where there's a bunch of T's that reaches a dead end if you work your way backwards, because that wouldn't make sense. How could this value of Aij be true if none of the subproblems it depends upon were true? It just wouldn't make any sense. So that would be our interleaving problem. But we're not done with this discussion of sequences. And so for the sake of just reminding ourselves that not everything involves strings of text, I want to define our next topic in terms of sequences of numbers. But I'd give it, I don't know, maybe 3 slides before I'm back to talking about strings of text. So let's consider a sequence S, which has all of these elements here. I want to talk about what's called a subsequence of S. So a subsequence of S is a sequence T that meets this definition. So remember earlier when I was talking about how using mathematical sequence notation, although nice and formal and crunchy, is pretty hard to read because of all the index variables? Yeah, I was talking about this slide here. So here is a mathematical definition of a subsequence. You're welcome to take a look at it. I think it makes sense. Explaining it and even writing it out is rather difficult just because of all the different index variables, and I've got indices of indices. So I've got like index I sub 1. So I'm going to use this definition because I think it's pretty clear what a subsequence is intuitively, but we have a formal definition if we need it. If we need to break a tie or to resolve a dispute, we do have it written down in formal mathematical legalese. Fundamentally, though, a subsequence, if I've got my sequence S and my sequence T, a sequence T is a subsequence of S if every element in T appears in S in the same order. It's not required that they be consecutive, but every single element must appear in the same left to right order in S as it appears in T. And of course, if an element appears twice in T, it has to appear twice in S. So that is, I'm not allowed to use the 6 more than once. The same number of things have to occur inside of S as inside of T. And of course, as this example illustrates, there is no requirement that a subsequence be a consecutive subsequence. Only that if I go from left to right through the smaller sequence, I do find every element in a left to right traversal in the same order in the larger sequence. All right, so of course, we could use sequences of numbers, but for the same reason as for the previous example, I think it's easier to use text because at a glance, it's much easier to see subsequences and sequences of text because I guess our brains are just better at reading text than numbers. And so, of course, because we're talking about sequences of anything, a sequence of characters is just as valid as a sequence of numbers for this problem. So we're talking about subsequences that occur inside of larger sequences. Now consider these two sequences. I've got the word greenhouse and I've got the word frosted. And suppose I ask for a subsequence that is a subsequence of both of these things. And we call the longest such thing the longest common subsequence. So there could be lots of sequences that are subsequences of both, but I would like one that has the largest length possible. Now there could be multiple, just to be clear. The word rose is the longest common subsequence of greenhouse and frosted. It has length 4. There might be other common subsequences of length 4. And they would all together be the longest common subsequences. So there could be multiple possibilities, but the longest common subsequence of these two things has length 4. And this is an example of it. I think it is a unique example. So R-O-S-E. So our task is, given two sequences, S1 and S2, where from this point forward I will assume the length of S1 is n and the length of S2 is m, determine the longest common subsequence. And so we want the actual characters in the subsequence. But it turns out, as we did before, that the way we're going to tackle this with dynamic programming won't be to devise a recurrence based on the characters' sequences themselves, but based on some easier to evaluate property. In this case, it'll actually turn out to be the length of the sequence, and then we work backwards from a table of values to find the characters in the sequence themselves. The same way we did with the interleaving sequence with our string interleaving problem. Okay, so that's our ultimate goal. I guess the first thing we should do is try a greedy approach. Because as I said, it tends to be the case that when you're given a new problem to solve, one of the very first things you do is try something that does amount to some kind of greedy algorithm. I think that this is a better illustration of a sort of classic greedy algorithm than the one I showed off earlier, because it seems as if the decisions I'm making can be justified as being sort of consciously, locally optimal decisions, versus in the previous algorithm for the interleaving problem, you could look at that and say, okay, but choosing which string to take a particular letter from isn't a locally optimal decision. It's more like a coin toss. So if the greedy algorithm makes a mistake, maybe that's just bad luck, versus consciously making a good decision. I think this is a more classic example of why greedy algorithms are a good thing to try, but don't necessarily lead you to a globally optimal result. So here's my idea of a greedy algorithm. I'll take one of my two sequences, let's say we use the top one, and I look at each character. And I basically say, I want to construct a subsequence that is common to both of my strings. So I'm going to ask, is A in that subsequence? Well, it's going to be in the subsequence if I can find it in the other string, and it looks like it's found in both. Because both strings have an A, I'm going to begin building a subsequence that begins with A. Okay, great. So I've got A in the middle, and it maps in like this. Okay, is B found in both of my two strings? Well, the answer happens to be no. Okay, well then B can't be part of my subsequence. Okay, what about C? And the answer is yes, there is a C in both strings, so I bring in the character C. All right, now I have a subsequence of length 2. Okay, I go and look for D. Now, remember that because the subsequence has to occur in left to right order, now that the C is in my subsequence, all of these characters are off limits. So I go look for the character D, and I say, well, of the remaining 2 characters of my lower string, D is not one of them, so I can't bring in a D. Same problem with E, same problem with F. Okay, so finally I look at the G, and I say, well, there is a G in both strings, and so I bring in the G. Okay, so there is a common subsequence. And you will observe this is in fact a common subsequence of both strings, and it has length 3. The question is this the longest common subsequence? This greedy approach that just tries to include every character it sees into the subsequence, did this produce the longest common subsequence? Okay, so I bring in A, and then I don't bring in B because I can't. I try and find C, and because C is in both sequences, I do bring it in. So I greedily try and include as many characters as I possibly can. If a character is suitable, I always bring it in. And then I bring in G. And the subsequence that I produce is ACG of length 3. But the longest common subsequence is actually longer than that. It has length 5, ADEFG. And maybe it's clear why the greedy approach failed here. It was on the C. So I went looking for a way of bringing in the C, and I found it. The C is over here. But by bringing in the C, I basically had to rule out ever using these other characters. And it turns out later that if I had skipped the C, so if I hadn't brought the C in at all, I'm going to go back to the blank version, if I brought in the A, but then I'd skipped over the C, then I would have been able to bring in the D, and then the E, and then the F, and then the G. The problem is the greedy approach tried to make a locally optimal decision. So at the point where it was considering the C, the only question it could answer is, well, if I add the C, then I get a sequence that's 1 longer. And if I don't add the C, then I don't get a sequence that's 1 longer. So what do I choose? Well, the greedy approach is make the sequence bigger. Always make the sequence bigger. So we greedily bring in the C, even though it turns out in this case, if we'd taken it easy and waited, we could have gotten a better solution by being patient. So the greedy approach, because it only looks at one state at a time, says, well, the C is viable, so we always bring it in. That is a locally optimal decision because we don't know whether any of the other characters will work. If we pass over the C now, it might turn out that the C was supposed to be present. And so all we know is that either we bring it in and that improves our solution, or we leave it out and we miss the opportunity to improve our solution. So the greedy approach is short-sighted. Even though it turns out that leaving the C out would yield a better solution, the greedy approach always brings the C in. And although we do construct a decent subsequence, I mean, we get a sequence of length 3, which isn't bad, the longest common subsequence has length 5. And so this is an illustration, although there could be other greedy algorithms out there, it's an illustration that, like with our string interleaving problem, if we try and make local decisions, we might miss the broader picture. We might see something that can be brought in, so I look at this character and say, wow, if I bring that in, I get an improved solution. I may not notice that if I bring it in, I'm actually ruling out an even better solution down the line, if I'm patient. And in a sense, the term greedy is sort of seen here as an antonym of the word patient. So a patient approach is one that considers the possibility that even though this might improve my local circumstances, it won't lead me to a globally optimal situation. And there are lots of cases where local optimum and global optimum are sort of opposite terms. They sort of fight with each other. A typical one, I guess, is the idea of in mathematical optimization, if you want to climb a hill. If I say to myself, I'd like to get to the top of a mountain, well, one option is to say, well, take a step that if I'm standing somewhere, then walk in whichever direction appears to be uphill to me, which means, so suppose that I'm standing right here, and I notice that if I take a step in this direction, I'm walking uphill. And then I notice if I can keep walking uphill, and eventually I reach a place where I can't go anywhere to keep going up. So I say, this must be the top of the mountain. But it turns out that from the point of view of my starting point, if I'd gone downhill a ways, then I would eventually have reached the actual top of the mountain somewhere up there. From the point of view of this starting point, the direction that appears to lead me uphill doesn't lead me to a global optimum, it just leads me to a local optimum. And a greedy approach sort of follows the same logic. So just like how in optimization, if you actually want to find the top of the mountain, you can't assume that if you walk uphill, you're always walking up the right mountain. The greedy approach, although adding the letter C might help a little bit locally, it might damage your solution globally. Now, as usual, even though the greedy approach didn't yield an optimal result here, we could use the greedy approach as the basis of a heuristic attempt to write a backtracking algorithm. That is, in a backtracking setting, sure, it's better to try the case where the character is in before you try the case where the character is out, because maybe you're going to get to a solution sooner if you do that. But in a backtracking algorithm, you leave the door open to the possibility that maybe you decide the solution is bad and you want to try the alternative where C is left out of the subsequence. But the greedy approach doesn't do that, and in so doing, the greedy approach ends up not producing an optimal solution. So we want to use dynamic programming. I mean, I'll save you the few slides where we build up to that observation. Of course, we want to try dynamic programming on this. And I will actually add that the longest common subsequence problem is one of the most classic dynamic programming problems as far as algorithm textbooks seem to be concerned. That is, if you open up an algorithms textbook, maybe it talks about subset sum, maybe it talks about the coins in a row, maybe it talks about string interleaving. But whether it does talk about those or not, pretty much every algorithms textbook ever that has a chapter on dynamic programming talks about the longest common subsequence. And to be honest, that might be one reason that I'm covering it here, is because it feels like it's something we all sort of have to know because everybody else seems to know it. So it's a good problem to cover for that reason as well. So it's something we can solve with dynamic programming. Now, as I mentioned earlier, we're going to try and solve a simpler problem first. I want to actually compute the longest common subsequence. The problem is, if you give me two strings, I don't know in advance how long the longest common subsequence is, and the size could be linear in the size of my input strings. If I use a recursive decomposition based on the strings themselves, that is to say, if I define a function called, I don't want to call it S or L. If I make a function called B, we'll call it C. If I make a function called C of ij that evaluates to the actual longest common subsequence of S up to index I and T up to index J, then if I make a table of these strings, I could end up wasting a whole ton of space because I might have a bunch of things in my table that are longest common subsequences corresponding to subproblems that I don't care about, and those sequences themselves could be pretty long. So instead, I'll do what I've done in earlier problems, where I develop a recursive decomposition for some easier proxy property of the problem. In this case, I'm going to use the length of the longest common subsequence. Not the sequence itself. I'm going to work out a table of values for L of ij. And the function Lij evaluates to an integer value, which is the length of the longest common subsequence of the first I characters of S and the first J characters of T. Because it's just the length, I know that I could make a table of values of L that's just an integer array, not some weird array of strings that could have a size that balloons out of control. Now, if I want to know the length of the longest common subsequence of my entire strings S and T, that would be the value LNM, where N is the length of S and M is the length of T. As before, I will also observe this sort of indexing snarl, which is that because Lij is the length of the LCS of S up to character I, up to but not including character I, and T up to character J, but not including character J, that means the last index of this string, the last character, is actually index I minus 1, and the last character of this is index J minus 1. So you'll notice minus 1's showing up in strange places later for that reason, because of the offset created by zero-based indexing. All right, so my base case is pretty easy. I'm talking about my function L, which is the length of the longest common subsequence. Well, if I want to talk about the longest common subsequence of S up to index I, and, well, if I'm talking about J equals 0, well, then T of 0, 0 is equal to the empty string. Which means I'm asking you, what is the length of the longest common subsequence of this string here and the empty string? Well, the length of the longest common subsequence of any string in the empty string must be 0. And so I have a pretty easy base case. L of I0 and L of 0j are always equal to 0. My recursive case is a bit more complicated. I'm going to break it into two pieces. And so I guess you can think of it working like this. Suppose I have two strings and let's say they run off into the distance here. I've got A, B, C, D, and then down here I have E, F, G, H. Okay, so I have two strings and this is going to be S up to index I, and this is going to be T up to index J. And one string ends in D and one string ends in H. Notice how the last character of the two substrings does not match. They don't match each other. So the question is, what is the length of the longest common subsequence of these two substrings? Well, we know that if H is in the subsequence, then D isn't, and vice versa. So these two do not match each other, and that means that one of them has to go. That is, the longest common subsequence will either be the longest common subsequence of this substring and all of the substring of T, or the longest common subsequence of this substring of T and all of the substring of S. And so we can actually break it into these two recursive cases. The longest common subsequence will either be the longest common subsequence of all but one character of S, if I discard the last character, or all but one character of T, if I discard the last character of T. And that means I realize if I care about the length, I obviously want the longest of the two lengths. So what I do is I figure out the length of the longest common subsequence of the first I-1 characters of S and the first J characters of T, and the common subsequence of the first I characters of S and J-1 characters of T. I just take the maximum, and that's the result in the event where the last character of the two things does not match. Okay, so there's one recursive case, and I appreciate that trying to describe that verbally or even in mathematical terms is quite a convoluted explanation, so just bear with me a bit. I think the examples will sort of settle this, and once we look at the finished recurrence, it'll be more clear what we're doing. Recursive case 2 is a situation where I have two strings like A, B, C, D and E, F, G, D. Okay, so the question here is, what's the status of this last character D? Well, it seems to me as if both strings match in that character, well then, if I notice that the longest common subsequence of what's left over has a particular length, then I could just add D to that longest common subsequence and make a sequence that's one position larger. We have to leave open the idea, I guess, the possibility that maybe if I just ignore one of the two Ds and leave the other one in, so suppose I get rid of the D in S, and then I consider the longest common subsequence of this and this, maybe this other D would still be useful as part of a longest common subsequence earlier on in S, or vice versa. So I suppose that means that in the case where the last character of the two substrings is equal, the length of the longest common subsequence is the longest common subsequence of all but one character of S and everything in T, the longest common subsequence of everything in S and all but one character in T, or the longest common subsequence that results from me getting rid of the last character of both of them, so subtracting one from both indices, and then plus the extra character that I know is equal, because I'm in the case where S of I-1 equals T of J-1. Yuck. Okay, so that means that the recursive case is this. The maximum of L of I-1, J-1, all plus 1, L of I-1, J, and L of I, J-1. Now, this observation becomes more clear when you look at the tables in a minute, but it turns out you can actually show, because of the way that the recurrence is defined, so because of the way recursive case 1 and the base case work, you can show via a bit of algebra and a bit of an argument, you can actually show that this entire expression always evaluates to this. So although formally we should consider the case where we don't include that last character in the longest common subsequence, it turns out that the value of L I-1 J-1 all plus 1 is always greater than or equal to either of the other two possibilities. So therefore this can be our recursive case number 2 by itself. That leads us to this recurrence. Now, as I said, the explanation that I just gave, even as I was giving it, I didn't really like it very much. I feel like this is the kind of problem where no matter how many diagrams you draw, it is actually quite difficult to get from the recursive observation all the way to the recurrence. Maybe the best way of doing that is to try and construct it yourself. There is one of the other stereotypes we associate with dynamic programming is that those dynamic programming algorithms are sort of write-only. That is, you can come up with one and write it down, but it's very hard to look at one and work backwards from it. And so I would encourage you as an exercise to, in a day or two, try and come up with this same decomposition yourself from scratch. Just reason it all the way out. Don't try and memorize it, just reason through it. I'll bet you could come up with the same one, and once you do, I'll bet you understand it a lot better than hearing my explanation. Because although I know where I'm going with this, and my examples I think show that what I've come up with works, I don't know that it's very easy to explain every step in a way that's very lucid, because it comes down, I guess, to how you think about the problem. In any event, here is the finished recurrence for Lij. So remember that Lij is the length of the LCS of the first I characters of S, so indices 0 through I, and the first J characters of T, indices 0 through J. And what I ultimately want is the LCS of NM. I want to know the length of that longest common subsequence and then work backwards to find the actual characters in the sequence. Okay, so our base case is when either of our two strings is empty, well then the longest common subsequence always has length 0. My second case is, as I said, the situation where we're working with two strings that do not end in the same character. Well, then it makes sense that only one of these two characters can be in the longest common subsequence. So in that case, the longest common subsequence length will be the length of the longest common subsequence of the case where I ignore the character at the end of T, or the length of the longest common subsequence where I ignore the last character in S, whichever of those ends up being longer. Okay, and then the third case ends up being the case where I have two sequences that end in exactly the same character, and I observe that what that's telling us is I could put this character in the longest common subsequence. So what I want is just the length of the longest common subsequence of everything left over. So if I subtract one character off from both, all plus 1, the plus 1 being from this D that is in the longest common subsequence. On the previous slide, I showed that we could also consider that maybe there's a way where the character D that is duplicated in both of them, if I leave it off, maybe I can still find the longest common subsequence of this and this, or symmetrically, I could find the longest common subsequence of this and this. It turns out, though, that in any event, the number I come up with will be less than or equal to that. So this can be our full recursive case. Here is some pseudocode to produce a table of values. So I create an integer array of size n plus 1 times m plus 1, and then I run two nested loops, and it's pretty clear, since what's inside those loops is constant time, that this algorithm is, again, big theta of n times m. And big theta of n times m isn't so bad for a problem like longest common subsequence, where we know there are lots of different ways to construct subsequences, only some of which might be the longest ones. And remember that n times m in the two-variable case is basically the two-variable analog of n squared. And n squared isn't so bad. There are lots of things that we do where we would love an n squared algorithm. So this is already looking like it's pretty fast. But all it does right now is compute the length of the longest common subsequence. What I want is the sequence itself. And so that brings us to phase 2. Given the table of values for L and a particular pair of strings, so I have this pair of strings, I compute the table of values for L, give me the LCS, give me the actual sequence, not just the lengths of sequences, but the sequence itself. And we know already that the way I'm going to do this is by using what I know about the recurrence, using what I know about the inputs, and using what I know about the problem to work backwards from this, the final problem I solved, which would be A10-7 or L10-7, work backwards to actually compute the elements of the sequence. And there are lots of ways of doing this. I'll actually show off two variations of the pseudocode at the very end here. There are ways that rely more on the inputs than the recurrence. There are ways that rely more on the recurrence than the inputs. I'm going to tend to try and use the matrix as much as possible. I actually want to develop a way of doing this that doesn't actually require me to know anything about the characters in the sequences, except when I finally go and pull the character into the sequence itself. So in other words, I'm going to find a way of computing which indices are in the longest common subsequence without needing to look too much at the characters themselves. Okay, so I work backwards from the value of L, length of S, length of T, or according to our indexing, L of NM. And so I know that the longest common subsequence has length 4. I notice that if I take the longest common subsequence of the entire string greenhouse, so that is up to and including index 9 of the word greenhouse, and the word frosted up to and including index 6 of the word frosted, so notice our usual indexing snarl, well this is actually column 7 of the table. If I do that, the sequence has length 4. But I also notice that L of 10-6, which is to say if I completely ignore the letter D, L of 10-6 is also equal to 4, which means that if I don't put D in my longest common subsequence, I can still find a longest common subsequence of length 4. So I'm good. So I basically can delete D from consideration. For all we know, there might be some longest common subsequence that includes D. Notice how the wording here, which I actually spent quite a bit of time coming up with, the wording here doesn't say that D can be eliminated from consideration altogether. It just says we don't need it. If we want a longest common subsequence, there is going to be one that doesn't include D, so it's easy for us to get rid of the D just to eliminate a possibility. There could be one that does include the D, and we could develop a different algorithm to go find it. We just need to find any longest common subsequence to solve this problem, though. Now, if I go look at element 10.6, which corresponds to these two E's here, so D is out of consideration, what I notice is that element 10.6 is greater than the thing to its left and the thing above it, which is telling me that if I ignore this E, or symmetrically, if I ignore this E, the length of the longest common subsequence of the two strings left over gets shorter, which is telling me that I should add E to my longest common subsequence, because if I don't, I lose out on part of the sequence. Okay, so the way that I can frame that is if the element at index ij is greater than the element at index I-1, j-1, and it's greater than both of its immediate neighbors, the one at index I-1j and index ij-1, if all those conditions hold, then I do want to add the corresponding character to my sequence. Now, the indices are correct in this example, so notice how even though I'm at index ij is 10.6, the characters I'm actually adding to my sequence would be index 9 of s and index 5 of t. So that would be index I-1 or index j-1. So I add the letter E to my longest common subsequence. Okay, then I take a look at this position, and I notice here that from this point of view, the longest common subsequence of these strings, the string up to the letter S and the string here up to the letter T, the longest common subsequence has length 3. But if I just ignore this letter T, if I move one column over, the longest common subsequence still has length 3, which means I can safely ignore the T. Okay, so I move back by one step. Okay, so now I'm looking at these two substrings, the word greenhouse up to the S and the word frost up to the S. And I see that they have the longest common subsequence has length 3, but if I ignore this row or this column, the longest common subsequence only has length 2, which means that it wouldn't be, that I shouldn't ignore this letter. This character should be added to my longest common subsequence, so I bring it in. And then I move up to this position here. And same, in this case, I see that the substring here is up to the letter U in greenhouse and up to the letter O in frosted. And I notice that if I ignore the U, that the length of the sequence does not decrease, so I can ignore the U, I just cross it off. Then I hit the O, and I see here that if I ignore the O, that the length of the sequence goes down. So I bring the O in, and I step up here. I notice that if I ignore the H, the length of the sequence remains the same. Same if I ignore the N and the E and the other E. I get to the R here, and I see that if I ignore this R, so if I go one column in or one row up, that the length gets shorter, which means I should bring the R in. And then I end up on this cell here, which is a 0. Notice how this position in the matrix isn't a base case. So normally I've been stopping my algorithm only when I hit a base case. I would argue here that I can stop early, because I've hit a position where the longest common subsequence of the substrings I'm working with has length 0, which means I'm never going to get any more characters into my subsequence again. So why not just stop? Why bother going all the way back to a base case? I could do that. I could crawl all the way over to the left-hand side or the top of the matrix, but I don't need to, because I know that there are no more characters available in my longest common subsequence. So that means my LCS is now complete. Okay, so I found the word rose, which I already said was the longest common subsequence of those two words. I have a few other examples here. These are just here for review. I really can't state strongly enough. I really want to telegraph that this is the kind of problem you need to know about for the exam. And this particular case of, given the matrix, reverse engineer it to find the longest common subsequence, yeah, you can be expecting to see that on the exam. Just so you know. And the examples I put in the slides, I put more examples than I need, mostly so you have lots of examples to study from, because I agree, I believe this problem is the kind of thing where it isn't difficult once you've practiced it, but there are lots of moving parts, and without practice, I think it's pretty hard to get comfortable with solving, with reverse engineering these LCSs. So I'll go through this one as well. Okay, so the first one is, I noticed that index 9, which corresponds to the letter G at the end, the LCS has length 6, but if I go up one row or over one column, the length is only 5, which means if I ignore the G, then I'm losing out, so I bring the G in, and then I bring in the N for the same reason, and then the I for the same reason, and then I move over a little bit, and eventually I end up bringing in the R, and then I eventually end up bringing in the P, and then the S, and then I hit a case which is 0, and so the LCS is complete. So the LCS of the words inspiring and sprouting is the word spring. Okay, what about the words abstracted and interface? Okay, so if I look at the lower right corner of the matrix, the length is 5, but the one above it is also 5, so I can just ignore that last D character. But then I have to bring in the E, and then I can walk up by one row, and then I bring in the C, and then the A, and then I walk over a bit, and then I bring in the R, and then eventually I hit this base, or then eventually I bring in the T, and I end up pretty far into the matrix still, but I end up hitting a cell that's equal to 0. So the length of the LCS at this point is 0, and therefore I'm done. And so the LCS itself is the word trace. Okay, now what about this? Here's an exercise, and in no uncertain terms, maybe make sure you can do this one by the exam. Like, other than blinking a red warning light and saying, I am going to put this exact thing on the exam, this exact one, there's nothing I could say to emphasize more strongly how important it is you know how to do this exercise. But here I have the table that corresponds to the values of L for the string S, which is the word mysteriously, and a string T that I don't give you at all. So there is some string T I used here, some string with actual characters. I'm just not showing you what it is. You're not given any of the values in the string T. Even so, I think you can find me the longest common subsequence of S and T. You have enough information to do that, so figure out what the LCS is. And then there's this version, where this is the matrix corresponding to the values of L for two strings S and T. But I'm not going to tell you what's in either of them. You don't get the characters in either S or T. Now, of course, if you don't know the characters in S or T, you couldn't tell me the actual contents of the longest common subsequence. But you could tell me which indices of S comprise the longest common subsequence, or which indices of T. You have that information available to you, so see if you can figure that out. A very good idea to try this exercise out before the exam. All right, and then here's some pseudocode for the reconstruction process. I've got two variants of it. And so it's actually, I think, the second one that better captures the logic I was using in the examples earlier. But basically the way that this works is we take the table of values of L, and we take our strings S and T, and we work backwards from the lower right corner of the matrix. One way of doing it is to observe that if the last character in S, last character of the substring of S, index I minus 1, is equal to index j minus 1 of t, then we must fall into the recursive case where that character is included in the longest common subsequence. So we add it to our sequence and then we decrement both indices. Otherwise, we either move up or we move to the left. That's one way of viewing it. The way that I did it in the examples earlier, though, was I didn't actually use the characters themselves. I just looked at the matrix. I said, if the current value of the matrix is greater than both of its neighbors, its immediate neighbors, so in other words, if the value in this cell here is greater than the cell to the left and the cell above it, that's telling us that we must have to go diagonally, and therefore that we have to include the character, so whichever character is over in each of our two input strings, that character is part of our longest common subsequence. So this is actually the pseudocode that I sort of prefer, because it's possible to reverse engineer the indices of the sequence, as you might do in that exercise from 2 slides ago. It's possible to reverse engineer it without ever actually looking at the contents of the sequences themselves, just by looking at the matrix. Obviously, to construct the characters of the sequence, you then have to go in and index the strings, but you don't need to know the contents of the strings to figure out which indices end up in the LCS. And I think that's useful not only because it shows off how much information truly is hiding in that table of values, but because it means that even if you are deprived of information about the contents of S or T, there is still a way of solving the problem. So that was a whole bunch of stuff about sequences, including some pretty convoluted stuff near the end there. So fortunately for us, we're going to go back to talking about optimization problems involving graphs in our next lecture. We're going to survey a whole bunch of algorithms for a really important graph-based optimization problem, including some algorithms that require dynamic programming.